It's you solve the equation.
All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Good. Right.
Good to hear it. Next week is Thanksgiving, so that's hopefully a good sign, right? So we're not going to see each other for a week, but and you know, this is usually the part where your professors say that, oh, you know, you guys get a week off, but you know, I know it's not like that. I know you're probably going to spend the Thanksgiving, you know, studying and working on projects and things like that. But you know, at least we won't have to meet for class, and there's no new information that week. You know, and hopefully on Thanksgiving Day that you can spend that time with your family too. Right? Maybe get some good deals on a Friday too. But you know, I think I'm too old for Black Friday shopping nowadays. Now I just do it all online. You know, I'm not too crazy about camping out, and you know, I used to see people like camp out in front of Best Buy and like have their Thanksgiving dinner there, and like I'm not into that at all. Okay, and so the subject for today is we have another ANSYS week. Okay. And so this is going to be our 7th ANSYS week. And so we've done a lot of ANSYS this semester. Okay. And the theme for this week is going to be vibrations. Okay. And so this is an exciting week. So I haven't done this in a class before. And so these set of lecture notes are new, and the activity that you're going to be doing on Wednesday is also brand new. And so I'm still working on the activity right now, just making sure that it's a good one. Okay. And then Wednesday we'll put it into action. Okay. All right, so in terms of announcements, so I think I might have forgotten to adjust the due date for this activity, and so activity 6, which is our optimization activity, I think on the on Canvas it might say that it's due on the 12th, which I mean not the 12th, the 16th, which is tomorrow. I'm gonna go ahead and push that back until Friday because I know the activity is a little bit of a time-consuming one, and so you know, and I'm probably not going to look at it until Thanksgiving break anyway, so. I'm going to push that back until Friday, so you have a bit more time to work on that. Okay. All right, and so I think that's all the announcements. I've gotten a couple people asking me about custom CAD models for their project, and so you know, definitely, you know, I'm open to that. The only thing is that, you know, for the people that have given me CAD models so far, the CAD models have been definitely on the more complex side, and so. You know, I'm not going to stop you from doing those projects, but you know, just be aware of the toll that's going to take on the computer, just in terms of, you know, how long it's going to take to mesh it, how long it's going to take to run the simulation. Because some of those CAD models, you know, it took me even just like 10 minutes just to load it up in the space claim on my computer. So, you know, I can only imagine how much time it's going to take to run the simulation. So, you know, if you want to do it, you know, I'm not going to stop you. Just you know, just make sure that you budget the time for that. Okay. Okay, I think that's all the announcements I have. And so are there any other questions I can answer before we get started? Okay, all right, so let's go ahead and get rolling. Okay, and so the theme for the ANSYS activity this week is vibrations and what is called modal analysis. All right. And so let me start off by saying that, so far in this class, we focused mostly on, I would say elastic failure of materials, okay? Okay. And what I mean by that is, we've so far in finite elements, most of the time we've mostly been concerned with, is this structure going to fail or not, right? And the main way that we determine whether a structure is going to fail is we compute, the maximum equivalent stress in the structure and compare that to the yield strength of the material. Okay. And so we've done this in both a static configuration, which is what we've focused mostly on. We've also done a little bit of dynamics as well. Okay. But this isn't the only failure mode for a structure, right? And so a structure can fail in other ways beyond this. Okay. And so one of the ways where a structure can fail, which is a prime concern for any kind of structural design, is resonant vibrations. Okay. Right. And so the whole idea with resonant vibrations is that every single object, if it has a physical form, it has what's known as a natural frequency. Okay. Okay. If you take this natural frequency, and if you excite, what we typically call it, if you excite the structure at this natural frequency, okay. Okay. And so what I mean by that is we apply some kind of oscillating load, some kind of variable load, okay? And the frequency of that loading is exactly the same as the natural frequency of the object. What can happen is that the amplitude of the response is just going to amplify and amplify and amplify, okay? And it's going to continue to amplify, right? And so what you're going to see is in some cases, is pretty magnificent. And so in some cases, what you'll see is that the vibrations and the amplitudes will just keep going up and up and up until the structure just can no longer sustain it, and then it all just kind of falls apart. Okay. And so this is the exact phenomenon. You know, if you're familiar with the party trick that some opera singers can do, where they take a wine glass and they just sing at it until it breaks, you know, that's exactly what's happening. And so what's happening there is that the opera singer is, you know, exciting the glass with the frequency of their voice that exactly matches the resonant frequency of the wine glass. And so that causes resonance to occur, and it causes the whole thing to shatter. Okay. Another very famous case that's shown in a lot of engineering classes is the Tacoma Narrows Bridge. So is everyone aware of the Tacoma Narrows Bridge? And so Tacoma Narrows is a bridge where, you know, they designed it without keeping in mind kind of the oscillating loads from the wind and from the cars that ran over. And so it very famously did, you know, really, really crazy motions until it all just kind of fell apart. Okay. And so, you know, with those in mind, you know, no structural engineer wants their structure to fail in resonance. And so, you know, being able to first of all analyze what the natural frequencies of your structure are, and then design your structure around that is a very core part of any kind of structural engineering. Okay, and so what we're going to introduce this week is, you know, the tools in ANSYS that are available to help you, you know, design around these phenomena. Okay. All right. Any questions on this? Okay. All right. And so what are some factors that, and so obviously, you know, the thing that we're most interested in here is, you know, we want to determine the natural frequencies of any structure that we're looking at. Okay. Okay. And ideally, you know, what you would want is that, you know, if you know the natural frequencies of your structure, these natural frequencies should not match or even come close to matching the frequencies of any loadings that are being applied on the structure. Okay. Okay. And a lot of times, you know, you're going to be able to compute the frequencies of your loadings, you know, fairly easily. And so as an example, you know, let's say that you're designing a bridge, right? And so it's a bridge which is designed for, you know, for people to walk over. Okay. And if you're going to have, you know, a fairly decent amount of foot traffic, you know, one frequency that you can avoid designing around is the frequency at which people normally walk. Okay. So this is a very common one if you're designing any kind of structure. Okay. And so, you know, another example is the building that we're standing in right now, right? So people are going to be walking around this building quite a bit. Okay. And so if you were the designer of this building, you know, you want to make it so that if everyone was basically walking up and down the hall at a particular frequency, this should not match the natural frequency of your building. Okay. Because if you do, then, you know, the building is going to fall apart just by people walking up and down the hallway, which is what you don't want. Okay. Right. So typically, you know, I say here that the natural frequency shouldn't match these loading frequencies, but in reality, you know, the way that designers avoid this is they try to design their structure such that the natural frequencies are way higher than their loading frequencies. Okay. And so let's say that, the walking frequency is maybe around like 2 hertz, okay? Average, so because people walk at different paces, but on average, let's say that we have a frequency about 2 hertz, okay? Ideally, let's say that you're designing a building, and so the natural frequency of this building, I would say, has to be at least 10, okay? Because you don't want to be, obviously you don't want it to be 2, and you don't want it to be, anywhere close to 2 as well, because things might happen where, maybe someone runs down the hall and then they're stepping at a higher pace, okay? And so you don't want to be kind of anywhere near that. And so there should be a decent factor of safety kind of involved here to make sure that you're never going to be around that case. Okay. All right. And so, of course, the key to this whole operation is being able to compute what the natural frequency of your structure is. Okay. Okay. But unfortunately, this is much easier said than done, because it's something that depends on a lot of properties of your structure. So it depends on its material, it depends on its geometry. To a certain degree, it also depends on its loading as well. Okay, and so this is normally not something that you can do by hand. And so this is kind of where ANSYS comes into play, right? And so the nice thing about finite elements is that it lets us do computations that are otherwise impossible by hand. And natural frequency calculations or modal computations fit in that category really, really well. Okay, and so today, we're going to discuss like some of the theory behind this, and what factors go into that, and what are some of the capabilities in ANSYS that allow us to perform this. Okay. Okay. Any questions on this? Yeah.
So if something like this is like so difficult and challenging that we have to use computer software, how did they do it before? Did they just like take weeks and weeks and weeks to get it done? And then
yeah. So before, it's, even though it's hard, it's really hard to get an exact number. You can do some decent estimates kind of based on whatever material that you're using, kind of the rough size of the building. A lot of times, what you'll see is that a lot of times these numbers depend on certain critical dimensions, like what is the thickness of the wall at this location. And with like kind of lots of experience and things like that, then they were able to get a good estimate. It wouldn't be exactly perfect, but usually good enough to do computations like this. And they would do a lot more scale testing too. So they probably wouldn't build an entire big building, but they would make a small scale one and then test their designs that way too. Yeah. Mm-hmm. Okay. All right. So let's talk about some of the theory behind resonance. Okay, so let's start with actually kind of the simplest case we can do, or one of the simplest cases, which is a string in tension. All right. And so, we're going to look at basically, what is basically a guitar string. And so we basically have a string that's going to be fixed to a wall. Okay. And so it's going to be fixed to the wall on one end. And on the other end, we're going to be supplying a tensile force. Okay. And so the string is going to be pulled tight, right? So imagine exactly a guitar string. Okay. All right. And so in addition to the tension in the string, we also know its length. And so we'll say that the length is L. Okay. And we also know mu, which is its density, but it's given in terms of mass per length. And so basically we know what type of material the string is made out of, and we know what its mass is per unit length, okay? All right, and so given this information, we can compute the natural frequency in the string. Okay, and so the natural frequency in the string is going to be 1 divided by 2 times L times square root of T divided by mu. Okay. Right, and this would actually be the lowest natural frequency. So this is the one with the smallest value. Okay. All right. And so let's take a look at the this formula here. And so even though it's fairly simple, we can actually glean a lot of information here that you know, is important for understanding resonance in general, and for, you know, what are some properties that we can look out for the you know, for our more complicated situations. Okay. All right. And so in particular, you know, I want to highlight these 3 parameters. Okay. So we have the length, we have the tension, and we have the mass per unit length. Okay, so let's go over each one individually, and let's extrapolate what they would really mean for a more complicated structure. Okay. All right. So let's look at number 1. Okay. And so number 1, we have the length, right? And so the length here is a geometrical property. In fact, it's our only geometrical property, right? And so what this tells us is that the geometry of the structure, you know, affects what its natural frequency is. Okay. Okay. And so whether your structure is really big or really small, has a lot of curves, not a lot of curves, has a lot of surface features, all of those things factor into, you know, what the natural frequency of the structure is going to be. Okay. And in fact, you know, what you see here is that the geometrical feature for this string is actually in the denominator, right? And so if we have a longer string, and so if we increase L, what that'll do is that'll decrease the natural frequency of our string. Okay. And so I want you to think about that, because, you know, part of the activity on Wednesday is I'm going to give you a geometry, and I'm going to give you a CAD model, and I want you to play around with some quantities like the geometry, things like the material properties. Okay. And I want you to have a good understanding of, you know, if I make this structure bigger, if I make the structure smaller, if I make the structure stiffer or less stiff, how's that going to affect our natural frequency? Okay. And so, you know, just kind of pay attention to the fact that the geometrical feature, or the size of the string, is in the denominator. Okay. All right. Next, we have the mass per unit length. Okay. Okay. Right. And so the mass also affects the natural frequency. Okay. And again, you know, we see that the mass here is in the denominator. And so what this tells us is that if we used a heavier material or a more massive material, then that's also going to decrease our natural frequency, and vice versa is true as well. Okay. Right. And our last category here, it's the tension. And this actually kind of represents 2 kind of main things. And so first of all, you know, this tension obviously is a measure of the load that's on our structure. Okay. Right. And so this tells us that, you know, if our structure is under a certain loading configuration, you know, that's going to affect its natural frequency versus, you know, if it was under a different loading configuration. Okay. And so another name that we can call this load here is called the pre-stress. Okay. And so the state of stress within the structure also affects what its natural frequency is going to be. Okay. Okay. Another way that you can interpret this tension here is that it's a measure of the stiffness in the structure, okay? And so, you know, we have another material property here that has to do with stiffness, which is the Young's modulus, okay? And so this tension here kind of represents both. And so it's not the perfect representation of these, but, you know, it's a string, you know? And so even though it's a simple string, you know, we have these three quantities here, and they kind of all, you know, fit into a certain category, okay? And unlike the other two, we see that the tension here is in the numerator, okay? And so what this tells you is that the more pre-stress that you have, or the higher amounts of load that you have, or the higher stiffness that you have, you know, this is going to make the natural frequency higher, okay? And so, you know, if you were designing a structure and your natural frequency is too low, you know, which is kind of the most common case that happens in practice, what you can do is you can stiffen up the structure. So you can either change the material to be something stiffer, or you can add more pre-stress into the equation as well, and that's going to, you know, raise your natural frequency. Okay. All right. Any questions on this? Okay. All right. And so the formula that I had on the previous page, you know, this is for what's known as the lowest natural frequency. Okay. And so by that sentence right there, you know, it implies that there's more than one natural frequency, and that would be correct, right? Okay. And in fact, there's actually infinitely many. And so basically what you can say is that once you compute the lowest natural frequency, all of the integer multiples of that frequency are also a natural frequency. And so, you know, in theory, you can have infinity. But most of the times, you know, that's not really that practical, because, you know, you can't excite something at like infinity, you know, hertz, right? You know, I don't care if you're the Flash or something like that. So that's just not possible. Okay. And so most of the time, you know, we're only really interested in the lowest one, or even the lowest two or three. But beyond that, you know, those are, you know, kind of nice to look at, but we don't really care. Okay. And so the lowest one actually has a special name. Okay. And so this is often called the first harmonic mode. Okay. And so if you excite the string at this frequency, you can actually view a very specific you know, deformation pattern. Okay. Okay. And so in fact, you know, the first harmonic mode for a string looks something like this. Okay. And so you just kind of have one big hump that goes throughout the entire string. Okay. All right. Another way that you can view this mode another way that you can view this mode is to apply an impulse loading, okay? And so what that means is that you apply loading for just a brief second, and then you just let it kind of vibrate on its own, okay? And so this would be kind of exactly the same as if you took a guitar string and you just pluck it, right? And so if you pluck a guitar string, if you have a guitar at home, I would highly encourage you to test this out. Or if you have YouTube, you can YouTube it. You can YouTube almost anything nowadays. And so if you pluck a guitar string, what you'll see is that the string stays vibrating for a little bit, right? And the mode of the vibration, if you look at it carefully, of course it's going to be going really fast, and so it's going to be vibrating kind of like this. But if you look at the overall shape of the mode, it's going to look something like this, because that's the most dominant frequency that that shows up. Okay, and so that's kind of another way that you can view this mode. Okay, and of course the frequency at which it's vibrating, right? And so if you pluck it and you let it go, the frequency at which it's vibrating at is going to be exactly the same as the natural frequency. Okay. All right. And so, that's the connection between like natural frequencies and, and the corresponding response. Okay. And so if you took the string and you vibrated it at this natural frequency, okay. And so let's say that you're an opera singer and you can look at a string and sing at this natural frequency. What you'll see is that the string will actually start to vibrate with that mode as well. And if you sing loud enough and you sing long enough, then the string will actually snap, because these vibrations are going to get higher and higher. Okay, it's going to look the same, and so it's going to have the same mode. It's just the amplitude is going to get higher and higher until the string can no longer sustain this, and then it just snaps. Okay. Right. And so usually, most of the time we're going to be concerned with the first harmonic mode, because that's kind of the lowest frequency that you can excite it at to get resonance. And usually if you're designing a structure, that's going to be the one that's going to cause your structure to fail. But there are other modes as well, and we'll discuss that briefly on the next page. Okay. All right. Any questions on this? Okay. All right, so let's discuss some of the other harmonic modes that are out there. Okay. All right. And so, like I mentioned, that the other harmonic modes, they are integer multiples of the first harmonic mode. Okay. And so if we call the second mode, we'll call that F2. We'll call that 2 times Fn, okay? Where Fn, remember, was our first harmonic mode, okay? And then F3, which is the third harmonic mode, is going to be just 3 times that first one as well, okay? And the mode shapes are going to be different for these as well, okay? And so let's look at F2 first, right? And so F2, might look something like this. Okay. Not might, it actually does look like that. Okay. So this is F2. And of course, I'm exaggerating these. And so, normally it does not this high. Okay. Okay. And F3 might look something like that. And so, for the strings case, it's very elegant in that the number of whichever mode that you're looking at also matches the number of bumps that you see. Okay. But that's what you can kind of expect to see, right? And so when we do our activity in ANSYS, what you'll see is that ANSYS will compute, let's say the first 6 harmonic modes for your structure, and you can actually have ANSYS show you, what does this resonant mode actually look like? And so, once you compute the resonant modes, you can tell ANSYS to show me what the deformation looks like, and it'll give you a deformation plot which shows you, what those modes are. Okay. All right. Any questions on this? Okay. All right, and so that's the simplest case that you can do in 1D. Okay. The situation, of course, gets a little bit more complicated when you add extra dimensions. Okay. Okay. And so for complex structures, what you'll see, and you'll see this in the activity on Wednesday as well, that some of the higher modes won't actually be integer multiples of the first one. Okay. Okay. And so, let's say that, our first mode here will be, let's say it's 300 Hertz. Okay. What you'll see is that the next mode might be something like, 347. Okay. And you'll be looking at that and you'll be thinking, what the heck, 347 is not 2 times 300, right? And so what's going on here? And so what's going on here is that for complex structures, you can have different resonant frequencies or different natural frequencies in different directions of the structure. Okay. And so, if we take kind of a very simple case of, let's say that we have a triangular block. Okay. Okay. And so, we might have our first natural frequency, might be in this direction right here. Okay. And so let's say that this is the frequency that's around 300 Hertz, right? We might also have another natural frequency in this direction right here. Okay. And that one's going to be independent of the first one because it's not acting in the same direction. Okay. Because it's a natural frequency or a mode that's deforming in that direction. Okay. This one might be something like 347, which is not an integer multiple of that one. Okay. But what you'll see is that each of these directions here kind of have their own kind of family tree. And so if we look at the next resonant frequency in this kind of horizontal direction, okay, then what you'll see is that this one will be 600, okay? Because it's in the exact same direction. And so, it's just an integer multiple of the previous one. Okay. All right. All right. Any questions on this? All right. Okay. And so, that's kind of what resonance is in general. And so let's talk about, what this means for ANSYS, what you can find in ANSYS, and what are engineers typically interested in finding. Okay. And so if an engineer is going to sit down and do vibration analysis, they're primarily interested in two things. Okay? And so number one, they're interested in what the resonant frequencies are. Okay, so that's the first one that they're concerned about. Okay. And number two, what they're interested in is, if we were to excite this structure at certain frequencies, what is the magnitude or what is the amplitude of the vibrations that occur. Okay. All right. And so thankfully, ANSYS has tools that can do both of these things. Okay. And they're going to be basically the subject of our activity. Okay. So let's go over point number 1 first. Okay. All right, so for point number 1, ANSYS has a tool called modal analysis. Okay. And so modal analysis is a tool that can find all of the resonant frequencies for a given structure. Okay. Okay. And so this tool is going to basically take the geometry into account. It's going to take the material properties, any kind of pre-stressing that you might be applying. It's going to take that into account too. And it's just going to spit out. And so you feed all that in, and it's going to spit out what the natural frequencies are. And it actually happens pretty quickly too. And so this is not an expensive analysis at all. Okay. All right. And so the only requirements, and so you actually don't even need to apply loads on this too. And so you can do what's called a stress-free modal analysis, where the only thing you have to do is you have to fix it in place. Okay. And so the only requirement really is a fixed support. And so you don't even have to apply any loads at all. Okay. Although generally it's more realistic if you do apply the loads, but that's not a requirement. And so if you as long as you fix it in space and you prevent any kind of rigid body motion, then you can perform modal analysis. Okay. All right. But if you do decide to add the loads, if you do decide to put any kind of external loads on the structure, this is going to add to the pre-stress of the structure. Okay. And so it's going to make your natural frequencies a little bit more accurate or a little bit more faithful to what it is in reality. Because if your structure is going to be subjected to some static loads, you want to account for that. But most of the time, the pre-stress is going to be fairly negligible. Okay. But a lot of times, it doesn't really cost you anything extra to include the pre-stress. And so, most of the time you're going to be doing a static analysis anyway. And so you might as well just use those results into the modal one and then, just call it there. Okay. And so with that in mind, ANSYS actually has a really nice feature where you can take a static structural simulation and directly link it to a modal analysis. Okay. And I'll show you how to do that on Friday. Okay. And so if you do that, this is going to automatically import the mesh. It's also going to automatically import your boundary conditions. So you don't have to re-add those in. And so you can just kind of work from there. Okay. And so that's really convenient because, you know, you can set up a static structural simulation and then you can directly link it to a modal one. And then you just hit solve and then it'll compute your natural frequencies just from that. Okay. All right. Any questions on this? Okay. All right. And so another nice feature of the modal analysis in ANSYS is that it actually lets you view the modal, the shape of the resonant nodes. And so if you were to do a simulation on a string, right, you can, after from the modal analysis, you know, you can tell ANSYS, you know, show me the first modal mode, show me the second modal mode, show me the third one, okay. I'll show you the fourth one. Okay. And so you can have ANSYS show you these, and you can actually see, you know, if you were to excite the structure at those frequencies, what the mode would actually look like. Okay. Right. I do want to make one really big, you know, word of caution here, and you know, even though I'm saying this, and I'll repeat this on Wednesday too, that, you know, someone is always going to ask about this. Okay? And so when you view these modes in modal analysis, just for illustration purposes, or just for visualizing purposes, ANSYS will tell you that, you know, it'll tell you that the magnitude of this deformation here, you know, might be like, you know, 1 millimeter or something like that. Okay. And so it'll actually have some numbers in there. It'll actually have some units. Okay. What I'm going to tell you is to not trust those units at all. And so those units are actually meaningless. Okay. Okay. So don't put any stock into those actual numbers. And so don't take a modal analysis and say, you know, if I sing at this gearbox at, you know, 300 hertz, then it's going to have, you know, exactly 12.443, you know, millimeters of deformation. It's not like that at all. Okay. So the only reason ANSYS puts numbers there is to help you illustrate, you know, what those shapes look like. Okay. And so don't take those deformation fields and say that, you know, this is how much deformation is going to be. It's not like that at all. Okay, because in order to actually get an amplitude of the deformation, what you need is some actual real you know, oscillating force. Okay. Okay. And in modal analysis, you know, we're not actually applying any kind of oscillating force, right? And so we might be applying some pre-stress, but those pre-stress are those are always just going to be static forces. Okay. And so don't confuse the pre-stress with, you know, with the actual oscillating force. And so, you know, actually applying an oscillating force and seeing how much vibrations you get, That's the next part. Okay. And so for that, you have to perform what's called a harmonic response analysis. Okay. But for just purely a modal analysis, you don't put any sock into the deformation. And so, it's mostly there just to show you what the shape looks like. Right? It's not meant for anything more than that. Okay. I will say that, ANSYS doesn't make it very clear. And so I think, I don't think it's that hard for them to, to put a warning or to put, some units on there that doesn't say millimeters, to say that, this is just dummy variables, but, that's really important to know when you're using this analysis. Okay. All right. Any questions on this? Okay. All right. And so, to set up a modal analysis is actually really, really simple. And so it's really only just one more step beyond a static simulation. And so, it's really powerful. And engineers can use this all the time, because what they can do is that, they can run a modal analysis really quickly. They could say that, hey, my resonant frequency or my natural frequency is really low. And so let me go ahead and redesign the structure so that my natural frequency is higher. Okay. And so even with just modal analysis, and what you'll see on Wednesday, that it's fairly simple to set up, you can get a lot of really useful information that you can use for your design. Okay. All right. And so I'll give you kind of one quick example of this. And so let's say that you're designing like a patio or a veranda or like a gazebo for a backyard. Okay. Or a veranda. Okay. And so let's say that, your shade looks something like this. Okay. All right. And so it's a simple just covering, that gives you some shade. Okay. All right. And so let's say that, the engineer designing this, let's say that he fixes it here, fixes it here, fixes it here, fixes it here. Okay. And let's say that the engineer designing this finds out that, the resonant frequency or the natural frequency of the structure is really low, right? And so, he applied he did a modal analysis and he found the natural frequency is maybe around like, 6-7 hertz. And, the wind that's going to be blowing on this thing is going to produce frequencies that are in that range. Okay. Okay. And so this might be a situation where, from a static point of view, this veranda might be structurally strong, right? And so, let's say that you apply like a wind pressure, he applied, maybe some fat bird sitting on it or something, and the veranda, holds its weight, so it's not going to fall. But, once he performed a modal analysis, he said that, this veranda here is not going to fail in an elastic kind of way, but it will experience resonance if I don't do something about it. Okay. All right. And so from the modal analysis, what you can say is that, I want to increase this, the strength of the structure. I want to increase this natural frequency. So let me increase the stiffness. Okay. And so let's say that he's going to add some crossbars here. And so let's say that he added a bar just like that, and maybe a bar just like that as well. Okay. And maybe for good measures, he added X's too. Okay. All right. And so he modified his geometry where he added these X's, and then he reran his modal analysis, and he found that, hey, my natural frequency went up, and so now I'm good. Okay. And so this is, oops, how did that happen? I didn't even touch my iPad. And so, this is one example where you take the results of a modal analysis and use them to design your structure for the better. Okay. All right. Any questions on this? Okay. All right. And so that's modal analysis. And so that's what we're going to spend most of our time with in the activity on Wednesday. But there are other tools that you can use in ANSYS to do vibration analysis. And one of the interesting tools that are available to you is called harmonic response analysis. Okay. Right. So harmonic response analysis will answer the question that we had before, is that, now that we know what the natural frequencies are, now we're interested in seeing, how bad are the vibrations going to get, or what are the magnitude of the vibrations that are going to occur, on the structure. Okay. Okay. And so this is another kind of tool that ANSYS has in its toolbox that lets you do vibration analysis. Okay. Okay. And so the big difference between harmonic response and modal analysis is that in this case, we're actually going to apply an oscillating load. And the main thing that we're going to have to specify here is what is the magnitude of this forcing that we're going to apply. Okay. All right. And so the resulting, and so to give you an example, okay, let's say that we have our string attached to a wall again. Okay. And so let's say that on one side of the string, we're holding it. Okay. Let's do the super long arms. Okay. So let's say that this person is holding the string on this side. He also has like General Grievous over here. Okay. So let's say he only has two arms. Okay. And so he's holding the string and he's going to choose, first of all, he's going to choose, how quickly he's going to pull the string up and down. Okay. Okay. But more importantly than the frequency, he's going to choose how high, how high he's going to move it up and down. Okay. Okay. Right. And so that's what you're going to have to apply in the harmonic response. Okay. And as a result, of this harmonic loading or this oscillating load, then the structure, which is the string in this case, is going to vibrate as a result. Okay. right? And so what we can compute in harmonic response analysis is what is the magnitude of that vibration response, okay? All right. Because a lot of times, the magnitude of the response is going to be different, sometimes higher, sometimes lower than the magnitude of the forcing, okay? And so I think it's easy to look at the situation and say that, this person is oscillating up and down with this certain kind of frequency and magnitude, okay? And so it's easy to kind of get sucked into the logic that, the structure is also going to oscillate with that frequency and magnitude as well, okay? But the thing with resonance is that if you excite the structure at the resonant frequency, then the magnitudes of the deformations can actually be much higher than the magnitudes of the force, okay? And that's exactly kind of what you can view from the harmonic response analysis, okay? All right, any questions on this so far? Okay. All right. And so what ANSYS is going to do is that after you supply the magnitude of the forcing, then ANSYS is actually going to test out this loading on not just one frequency, but it's going to test it on a range of different frequencies. Okay. Okay. Right. And then so for each of those frequencies, then ANSYS is going to measure what the magnitude of the resulting vibration is going to be. And so for basically each of those frequencies, you're going to get a magnitude of the vibration. Okay. And the way that ANSYS basically shows this data is through a plot known as a spectrum plot. Okay. Okay. And so if you've never seen a spectrum plot, it looks something like this. Right. And so on the x-axis here, we have the frequency, which usually has some units of hertz. Okay. And on the y-axis right here, we have the magnitude of the vibrations. Okay. Which from now I'm just going to label it as deformations. All right, and so a typical spectrum plot might look something like this. Okay? Okay. And so you're going to see a plot where basically you have these kind of very well-defined peaks. Okay? Where these peaks are going to be your natural frequencies. Okay. And so basically, what you can see from this spectrum plot is that when you force or when you apply an oscillating forcing at the natural frequencies, it's going to result in very high magnitude or high amplitude vibrations. Okay, and so that's what the peaks here represent. But if you if you don't excite your structure at those frequencies, the magnitude of the vibrations are going to be off. Okay, right, and so you're going to be somewhere over here. And so ideally, what you would want, for this first natural frequency, remember, we want this first natural frequency to be so much higher than, the actual frequency of the loading, okay? And so in most situations, you want to operate in a range over here, where this boxed area, this is the frequency of your typical loading. Okay, and so remember, you want your typical loading frequency to be much lower than your natural one. Okay, that way, because otherwise, if you, it's very easy to say that, what if my loading frequency is over here, right? And so here you're kind of playing a little bit of a dangerous game because, you typically don't want to be in between the peaks. You want to be in a region, before a peak even occurs. Okay, and so a lot of times you want to be where the box is, not where the circle is. Okay. All right. And so one quick note before we wrap it up today is that the harmonic response that you view here, of course, is going to depend on the direction. Okay. And so one feature that you can look into when you do harmonic response is you can change the direction of the loading. And so if you apply the load, in the X direction, you're going to get a certain spectrum plot. But then if you apply that load in the Y direction instead, that's going to give you a different spectrum plot. Okay. And so you can adjust that just to kind of see. Okay. And another thing is that in order to perform a harmonic response analysis, you have to perform a modal analysis before this. Okay. Because in order for in order for ANSYS to know where the peaks are going to be, it needs to have computed those beforehand. Okay. And so when you perform a harmonic analysis, what you'll see is that we're gonna link that directly to a modal analysis. Okay. All right. Any questions on this before we wrap it up for today? Okay, all right, and so that's all I got. And so, I did end up being a little bit early, but that's okay. Okay, and so there's not too much to say about modal analysis and vibrations. And so on Wednesday, when we meet up next time, we'll see all this put into action in ANSYS, and we're going to do our activity. Okay, all right. So thank you everyone for tuning in today. Hope you guys enjoyed the lecture today, and hope you guys have a good evening. And I will see you on Wednesday for our activity. Final template. I'll do that this week. Yeah, thanks for reminding me. I kind of forgot about that. So yeah, I'll do that this week, and I'll upload it. I'll have it uploaded on Canvas before Wednesday. Yeah.
I got a question.
Yeah.
So I'm on problem 5.
Yep.
I've optimized with the information and stress now.
Okay.
And this is my counting point, but I'm wondering what the 0% means. Obviously, these are different inputs than the original.
Yeah.
But what is the 0%? So what is X and minus 0%?
Yeah. So the 0%, what that means is how much it changed from your reference. And so the reference was kind of the starting point. Actually, no, I'm sorry. So the reference is whatever is the best one.
Oh, okay.
And so it's going to be 0% for the first one because that's the reference.
It's referencing itself.
Exactly. And so the percentages here is how much different it is from that. So if you look at where is it? The way I compute it for the maximum deformation, and you're trying to minimize this.
Yeah.
And so this one is 2.1% higher than the reference. And so that's why they picked these three because it's required to pick 3. And so we said this one was the best one, and then these ones are close-ish. And so I think the X's mean that it wasn't able to find something that it thinks it's good. And so we said that this is the best I can do, but it's not great. And so the minus means that, it is able to approve it. So that's why these two you see minuses, because those are in pretty good range. But you can see this third one is X because it's 1 or 2. It's going higher.
That's weird because when I look at this,
Mhm.
this is actually better than the normal definition. So I don't know why it's giving me that. It should give me like a check mark.
Yeah.
Or no, it should be like a minus.
Yeah. So it tries to do, a target for that. And so even though it's better than the original one, it's still trying to reduce it by a certain amount. And so it's trying to reduce it by that much. I think the X's here, and I have to double check, but I think these are also kind of based on your targets too. Remember when you set the targets, you can say minimize, and minimize, you remember we said that, we're trying to minimize it to 0.
0. Oh.
And so this is saying that, I couldn't even get close to 0, relative to reference. And so,
Okay. So,
and so
if I did 0.03, then it might say
yes,
close to it.
I haven't tested that, but I think but I'm pretty sure that's what it means, kind of just based on what I've read. But yeah, I always thought X's are much. But, if you ignore the X's because you want to minimize it as small as possible anyway, then that's interesting.
Sometimes there's 2 X's. What does that mean?
That means it's really bad.
Okay. Okay, thank you so much.
Yep.
Professor, are you gonna mention about moving?
I mentioned at the beginning.
Oh, did you?
Yeah.
Okay.
I'll put out. I'll put out an announcement when I get back.
All right.
Yeah, it'll be due Friday.
Okay, Friday?
Yeah.
Okay, all right, thanks.
I got a quick question.
Sure.
I'm gonna need you to look at mine.
Okay.
You check.
Okay.
Yeah, so for this activity, you know how we initially found the definition of just before we did any kind of optimization?
Yep.
And we were supposed to have, I think we were pretty similar, like 36.
Yeah.
So after I did optimize it, those values went slightly up.
Sometimes that can happen.
Okay, so that went up like.
This is the default one we did in the class.
Correct.
So it was trying to optimize on the mass.
Correct.
So those two are competing. So
That's what I figured.
Yeah.
So, I mean, you set bounds to the math, right? I'm assuming it's going to, it should try to meet those.
Yeah.
Right, and depending on it trying to meet those bounds, the definition might need to go up. slightly. Okay. Okay, that was my explanation to it, because I know the math decrease, right? 'Cause we're
Yeah.
trying to,
Yeah.
So I think due to that increasing, like because of the radius did increase here and it has like a larger surface area to allow for more, I guess, stress concentrations there, it did increase the definition a little bit.
Yeah.
But I mean, I think the mass increased significantly, so the width.
Yeah.
I just kind of like concluded that a little bit something with design.
Yeah.
Make a decision on the stress concentration.
Yeah, so when you have competing factors like that, it's going to choose, that's why it gives you 3 points, because the 3 points, because it accounts for things like that. And so it says that I did pretty good on this target here, but not so good one here, and then pick another one.
So it will always be the balance you set.
Yes.
And then
It'll
it'll try to
always be.
minimize it as much with meeting those bounds, and that could end up being a certain percentage. Okay,
Yeah, it'll be, I mean, the one we did, with only a 2, I think for the cost. That one's not, I wouldn't say that's not a true optimization because it kind of just scatter shot all the parameters.
Yeah.
So true optimization, what you do is that you kind of run a few tests first. And you get some results. Okay, so maybe I should go in this direction. But it didn't really do
based
that.
on your original results, like,
Exactly.
okay, I'm getting, the kind of definitions or what's
Exactly. Exactly, but if you could tell from this one, you say, only run it with a 2, it determined all the points that it wanted kind of before it even did it. And so that's not really a true deformation, but a true optimization. But if we did a true one, you'd be sitting here for hours waiting for the result. And I didn't want that too. So.
When you say running by 2, you're talking about the time? You're not talking about the design points, right?
No,
The
the time. Yeah, so the time. So that's the rating that you can get from 1 to 9. So based on how expensive they want. Yeah.
Well, regardless, your design points are chosen based upon however you validate your inputs, right?
Right.
So say you have, 41 design points, right? But you chose the time to be 2. What does that change? Because the design points remain the same.
So if you change the time, then it'll change the algorithm. And so right now it's kind of running an optimization where it just kind of scatter shots different design points. And so it said your bounds are this, and so let me just pick randomly between these within these bounds, and we'll just find the best one. But different optimization algorithms that let me run this cluster first. So let me run like maybe 10 design points, And then from there, it gets an idea of, okay, when I do this, it's going to modify this and this. And then it's going to try to pick the next set of design points more intelligent based on, try to get you closer. Instead of just doing random stuff. But that's a lot more expensive. So I didn't want you guys to know.
Is that, can you consider that like equivalent or somewhat like in parallel to like the amount of nodes you have?
Kind of, yeah.
Because depending on how complicated you make the hash, you know, apply X amount of nodes from that, which means that you're applying, you know, that quadratic equation to each one of those nodes. More of those data.
Yeah, you can think about that.
Okay. All right, well, I guess I will. And you said it's due Friday now?
Yeah, you're right.
So I don't have to rush to finish this, right? I thought it was due tomorrow and I.
Yeah, I forgot. I think I meant to change it before last week, but it's kind of. So,
Yeah, I mean, I've been kind of just running it and then doing.
yeah, that's the nice thing about optimization.
Okay, cool, I appreciate it.
Are Rams winning?
They are currently losing.
Okay.
Yeah.
I saw they got Odell, but then Robert Woods got hurt.
Yeah,
He entered that.
This is a give one, take
What was
one
that?
type of thing, yeah. But I mean, they got Von Miller on defense too. So
Oh, he's
they're-
good. He's good. He's back now.
Yeah, well, yeah, so they just activated this game. I
Okay.
just bet my friend who's a Rams fan, $200 that they wouldn't win the Super Bowl. Like, so
Uh-huh.
not just make it, but win it, right?
Uh-huh.
This is pre Odell Beckham and Von Miller. Like, this happened like all in a week. I'm like, did they like, hear me make this freaking bet? And they're like, you know, we're gonna get all these guys. Yeah. All right, Professor.
Yeah.
See you Wednesday.
Right, see ya.
We're just re-optimizing what was already optimized, right?
Yeah.
Mhm.
Not going back from the to the original.
No. So you can just re-optimize what's there, but
Because
you
at
can.
this point, it doesn't even look like the same. You know what I mean? It's-
Yeah.